Welcome to the 15th lecture of the course Marine Propulsion. Today we will be discussing methodical propeller series. Methodical series data are used for different performance assessment of marine propellers. So, these are also called standard series or systematic series data, which are developed based on experimentation on a number of propellers of varying characteristics. So, if we have a particular propeller type and then by varying the parameters in a systematic way, a series can be developed, and that has been done over a wide range of parameters to have a basic data set which can be used for design of propellers. So, in terms of parameters, the primary parameters which are varied to obtain these data sets are the number of blades, pitch ratio and blade area ratio, which are very important in defining the propeller geometry. And there are other details, for example, shapes of blade section and other aspects like thickness ratio, which are normally unchanged. So, keeping these parameters unchanged, the parameters like number of blades, pitch ratio, blade area ratio are changed in a systematic way, and then for a particular design experimentation is done, and based on those obtained open water characteristics the methodical series is defined, and these methodical series data are widely used in obtaining propeller design for specific conditions. So, if we have a requirement, sometimes for preliminary design it is also very useful to have a first hand idea of what the design should be. So, these data can be interpolated to get the results or the final design for a specific configuration between the values which are experimented for all these parameters. So, if we think of the database for designing a propeller, certain factors are important, and having a methodical series data gives a first hand estimate to finalize the propeller dimension. So, when we discuss propeller design later in this course, we will see that there are different parameters which impact the performance of a propeller. So, the geometric parameters which impact propeller design vary from pitch ratio to blade area ratio, camber, thickness, blade section and number of blades. In a typical methodical series, some selected parameters are varied, and this helps in making the design process easier. So, if we think of a particular methodical series, all the propellers belonging to that series are somewhat related to each other by these series of parameters, because certain aspects are constant in terms of the geometry of the propeller blade. And when we have the open water characteristic for a set of propellers in the series, so if we have the limits defined by a specific series, we can obtain the characteristics of any propeller within the boundaries of those limits for the specified parameters, which we will try to understand when we go into each of these series. So, this is a typical example of open water test results which are obtained by varying the P by D ratio. So, if we have a particular propeller geometry and the number of blades AE by A0, the blade area ratio constant, then just by varying the pitch ratio of the propeller blade we can obtain a set of curves. Now, if we remember, the x axis in the open water diagram is J, which is the advance coefficient Va by Nd, and the y axis has Kt, 10 Kq and the open water efficiency. So, in these diagrams we have the Kt curves, 10 Kq curves and the eta O or the open water efficiency curves. So, now if we see here, by varying the pitch systematically, the diagram changes. So, this concept I will explain in more details when we talk about controllable pitch propellers, but the basic idea here should be understood that if we increase the pitch of the propeller blade, here represented by the pitch ratio. So, if we go from a value of let us say 0.7 to a high value of 1 P by D ratio, what is the effect on the KT, KQ and eta O? First, by increasing the pitch ratio, the angle of attack of the blade section increases. If we think of the blade element diagram, the face pitch angle defined by phi is a function of the P by D ratio. Now, as we increase the pitch, the angle of attack for the blade section will increase and the thrust and torque value will also increase. So, as we increase the pitch, the KT and KQ values are increasing. In that way, the efficiency also has a wider range, because the KT KQ curves go to 0 at higher values of J here as the pitch is increased. So, the open water efficiency, the entire operation range increases, but the efficiency is not always higher if we increase the pitch. So, for example, if we look at a point here and take a point here, okay. So, the efficiency for P by D equal to 0.9 is this. The same here will be lower compared to a case where P by D is equal to 0.5 or 0.6. So, the efficiency range or the operation range increases as we increase the pitch. So, we can say that by varying the pitch ratio, a systematic series of open water diagrams can be constructed for a specific propeller geometry. So, based on these concepts, certain propeller series have been developed. For example, Gone series, the B series or the Wageningen B series developed at Marine in Netherlands, also called the Truss series sometimes. It is one of the most widely used propeller series for different purposes. KA series, it is the Kaplan series, also developed in Marine and specifically used for ducted propellers. These aspects of KA series with ducts we will study under ducted propeller. And Mao series is a propeller series developed in Japan. So, we will briefly look into Gone series and B series in terms of methodical propeller series here. So, for the Gone series, the blade type is segmental blade section. So, the blade sections which are used are segmental in nature, which we have discussed in propeller geometry, and the developed blade outline is elliptical. So, as every series I have mentioned has certain variables which are varied. So, certain parameters which are varied and certain parameters which are kept constant, which are specific for that series. So, here we will see in the Gone series the variation is on the pitch ratio P by D, which varies from 0.6 to 2, and the blade area ratio, which is defined by the developed blade area in this particular series divided by the disc area, is varying between 0.2 and 1.1. So, based on these, a range of open water diagrams are constructed which can be used for analyzing and designing propellers under these particular series. Now, for B series, a typical nomenclature is like this B440, where 4 the first digit corresponds to the number of blades Z, and the second one 40 divided by 100, that gives the AE by A0, the expanded blade area ratio, that will be 0.4. Okay. This is how B series propeller nomenclature is done. So, here the blade type is asymmetric blade outline, and airfoil section is used at the inner radii and gradually varying into segmental sections at the tip. Now, because at the tip there are higher chances of cavitation, that is why segmental sections are used, which has certain pressure characteristics which is more conducive towards the tips. That is why for B series propeller a combination of airfoil and segmental sections are used. Now, B series propellers have a huge database varying from blade numbers 2 to 7 blades, and for each case different P by D ratios are investigated. So, these series are developed based on experimental results on model propellers over these ranges of parameters, and in during design, which we will discuss later under propeller design, we can use these data to get our specific design based on the input requirement by suitable interpolation using certain constraints which are essential for the design process. Now, AE by A0, here the expanded blade area ratio is used in denoting the B series propeller area, and for these different kinds of blade numbers, the AE by A0 ranges are shown for each case. Let us take two cases for number of blades 3 and number of blades 5. So, we will see that as the number of blades increases, the naturally there will be an increase in the blade area, because the disc area A0 is defined by the diameter. A0 is nothing but pi d square by 4, where d is the diameter of the propeller. So, if we increase the number of blades within the same area, if we try to put more number of blades, what will happen? The basic AE by A0 will increase, that is what is shown here. As the number of blades increases, the AE by A0 range is different. Now, T by D is the thickness ratio which is kept constant for a specific case which belongs to a specific number of blades. So, for each case you will see T0 by D and D by D is the ratio of the boss diameter to the propeller diameter. So, these ratios are kept constant. So, the only things which are varied are Z, P by D and AE by A0, and this chart is shown as variations of P by D and AE by A0 for a specific Z. So, if we combine this entire data set, it gives a wide range of variations of these three parameters, which forms a database based on which propeller characteristics in open water are presented and which can be used for design. So, again just like the one that we have seen, variation of pitch, let us take a B series example. We have a propeller with 4 blades, AE by A0 of 0.45, and we try to see its open water characteristics for a range of pitch ratio P by D of varying between 0.5 and 1.2, and these factors T by D and D by D are constants as mentioned. So, if we look at the open water diagram, as before we have kT 10 kq and eta o as functions of j, the advance coefficient, and as the pitch ratio increases, the kT and kq in the open water diagram will increase, that we have discussed just now. And similarly, the open water efficiency values will reflect these changes in kT and kq for different pitch ratios. So, now if we take another value of A by A naught, if we go back, let us say we take a value of 0.5 which is between these values. So, if we take another value here of 0.55, then we will get a new series of kT, kq and eta o versus j. So, a new set of open water curves will be generated in the same range of p by d. So, this particular diagram is valid for AE by A0 equal to 0.45 and Z equal to 4. So, if we go from this to any other basic constants, for example, if we take Z equal to 5 or Z equal to 6 or keep the j constant and change the A by A0 value, then this entire diagram will be changed, and that will again create a new set of curves which will be part of the larger data set. So, instead of these curves, polynomials can also be used to represent the values of kT and kq in the open water condition for a range of values of pitch ratios, blade area ratio and number of blades. So, they are represented using these equations where kT is expressed as functions of j, p by d, A by A0 and z, and these coefficients Ct and similarly for kq we have Cq will depend on these 4 parameters. So, for a specific set, these coefficients are calculated based on regression analysis of all the experimental data for kT and kq for these change of parameters for specific designs. So, these B series open water diagrams can be represented using these polynomial expressions for kT and kq, which can be used in propeller design. Now, if we look at a simple problem which can be done using B series or any methodical series data. So, for this we have been asked to determine some parameters for a propeller for which the thrust, RPM and velocity of advance is given. So, the requirement of thrust to be delivered at a particular RPM for a particular speed of advance is given, and we have to determine the optimum diameter, pitch ratio and the delivered power in the open water condition. So, this is not a proper propeller design problem, this is just an example to use the open water charts, KT KQ charts simply to arrive at a particular optimum design for specific requirements. So, what we can do here is the thrust, RPM and advance velocity is given. So, if we think of these factor, KT has a term propeller diameter in it and J also has propeller diameter in it. So, if we take KT by J to the power 4, it gives T by rho n square d to the power 4 and V a to the power 4, right. So, here what is simply done is the diameter is eliminated, because it is an unknown that we have to find in this problem. So, this gives T n square by rho V a to the power 4. So, from the given data we can calculate this expression, because the thrust, the rotational speed and the velocity of advance is given. So, if we do that, we can use this to calculate k T for different j values. Now, we can use the series data. Here it is implied in this problem that the series data for a range of pitch ratios are available. Okay. So, this is just a sample problem which I am using to explain how we can use series data to arrive at a simple design using the open water diagrams. So, from these KT, KQ, J diagrams or polynomials, we can find the intersections with this KT versus J line for each pitch that we have defined for a specific KT by J4. Now, using similar lines for KQ versus J, the KQ as well as open water efficiency eta O can also be calculated, because we already have the open water diagrams for the propeller series. Now, we have to choose the pitch condition for the given case where we have the highest efficiency. Now, these KT by J to the power 4, this intersections with the KT, KQ, J diagrams will correspond to a particular point for every P by D. Now, technically we can choose any of these points as a suitable design, but normally in propeller design we will try to go for the option where the open water efficiency is highest, if there are no other constraints. Here we are not given any other constraint. So, we will choose the pitch condition for which eta O is maximum from these intersections. Now, once we choose that, so we already have calculated the optimum pitch ratio for which eta O is maximum, then we only have to calculate the optimum diameter and delivered power. Now, for that corresponding condition, if we calculate J, then using that J we can calculate J is V a by N d. So, the diameter is J into N by V a. So, the optimum diameter can be calculated next, and finally, the delivered power can be calculated using the KQ value or the torque coefficient for that specific J. Okay. So, we choose the P by D ratio based on the maximum efficiency from the given set of curves, and from that we get the value of J and finally calculate the power using the torque coefficient. Now, we move on to some other charts or propeller coefficients which are used extensively for propeller design. One such example is the BP delta chart developed by Admiral Taylor, where the coefficients BP and delta are given in relation to the propeller RPM, diameter, the delivered power and the advance speed. Here the system which is used is the British system. So, PD is the delivered power in British horsepower and VA is the advance speed in knots, whereas you have the propeller diameter in feet and n is propeller RPM. So, for a specific problem, when we use these charts, we have to convert the case that we are designing into these units, and then the BP delta chart can be used. So, in the BP delta chart, we have the BP and delta as functions of these parameters for the propeller. So, in this particular equation, delta is nothing but the inverse of J, expressed as Nd divided by velocity of advance. So, these charts are preferred when the advance velocity, RPM and delivered power are known, and we have to design the propeller in such a way that the diameter and P by D or the pitch ratio are unknown, and these will be the outcome of the design, and we have to look for the case with optimum efficiency. So, when we do B series propeller design under the propeller design part of the course, then I will show these charts and explain the concept of optimum efficiency and how it can be used in propeller design. Another diagram which is used for propellers operating at very high loading is the mu sigma diagram. So, very high loading means we have very small j values, because the propeller loading is high when the j value is low, that means the kT and kq is very high. So, the thrust loading is high. So, in these conditions delta becomes very high, okay, because in the BP delta diagram delta is basically the inverse of j. So, obviously for very high loading the delta value will be high and will fall outside the range of the standard BP delta diagram. So, for those cases mu sigma diagram are used, and these coefficients are also used for propeller design for vessels where the propeller loading is very high. So, the coefficients which are used in this particular diagram are given here as functions of kT, kq and j, the advance coefficient and the thrust and torque coefficients in open water. So, these coefficients are used in designing propellers with high propeller loading using this mu sigma diagram. So, this will be all for the methodical series part, and this ends our discussions on propeller in open water. We will continue with propeller behind hull in the next class. Some references which can be used in general for propeller in open water and also for the B series propeller are given here. Thank you.